Hi everyone, welcome to this lesson which is about the sine rule. Now I've got here a little GeoGebra page that I'd like to talk about for a few moments. I have a triangle. The lengths of the sides A, B and C are marked. Remember the length of the edges are indicated by lowercase letters. And I have the angles A, B and C. Remember angle A is opposite to side A. Angle B is opposite to side B, and angle C down here is opposite to side C. Now, a very long time ago, some clever people figured out that if you went A divided by sine of angle A, so in this case 10 divided by the sine of 90 degrees, that came out equal to 10. And they then checked, what happens if I go B divided by the sine of angle B, so 6 divided by sine of 36.7 degrees also came out to equal 10. Now that seemed like a coincidence, so they thought we should check for angle C. So little c, 8 divided by the sine of 53.3 degrees also came out equal to 10. Now that seemed too good to be true. And they thought, well, perhaps this is only working because I have a right angle triangle here. So let me just move this point. And this is the nice thing about GeoGebra. As I move the point, all the edges and angles are remeasured and all of the calculations are redone. If you check, pause the video and check that the numbers that have changed here still match. Side A, angle A, side B, angle B, side C, angle C. Now they don't all equal 10 anymore. This time they all equal 7.9. It's not so much that they equaled 10 that was the good thing. The fact that they all equal the same is the exciting part of this. So in any triangle I care to draw, it can be a scalene triangle like the one I have here. It can be a right angle triangle. It can be an obtuse triangle where one of the angles is an obtuse angle. It doesn't really matter. Any triangle at all, A divided by sine A plus equals B divided by sine B equals C divided by sine C. It doesn't really, we don't really get too worried about what number that works out to equal. We get excited about the fact that all three of these are always equal to each other. And that's the sine rule. Now if I put that away over there for a moment, and I have a little error message, so take that away, I can use the sine rule to solve questions like this. So let's have a go at this. It says find the unknown angle and side lengths correct to one decimal place for a triangle ABC. They've given me some of the information, but not all of the information. Now the most important step is to draw a diagram. And I will label capital A, B, C for the vertices, and then remember lowercase a will be opposite. We don't have a side for that, so that's unknown. Lowercase b will be the side opposite point B, and that's equal to 8. I don't have a value for lowercase c. I do have that the angle at B is 75 degrees, and I do have the angle at C is 70 degrees. Now, I do not know the angle at A, this one. I do not know the length of C, and I do not know the length of A. They're the three things that I need to figure out if I'm going to solve the triangle. The question said, find the unknown angle and side lengths. So I have three things to find. Now, I will use the sine rule. The sine rule, I won't go with A over sine A. Both of those are unknowns. That would be difficult if there were two unknowns. But I could go B divided by sine of B equals C divided by sine of C. Let's do that. B over the sine of angle B equals C divided by the sine of angle C. Now I don't need all three parts of the sine rule at the same time. Any two parts of the sine rule work nicely because remember all of them always equal each other. And in this case little b equals 8 over the sine Angle B was 75 degrees. I don't know little c, but I do know that angle at C was 70 degrees. This gives me an equation that I can use to solve. If I multiply by sine 70, I'll have 8 over sine 75 degrees multiplied by sine 70 degrees should equal little angle C. Now, if I'd been a bit more organised, I would have had my calculator ready, but just bear with me for a second while I find my calculator. It'll be here somewhere, almost there. There it is. So check that it's on degrees, yes, and I need a fraction. I need 8 over the sine of 75. Then move to the right and multiply by the sine of 70. That looks right. And my answer is 7.78. They said one decimal place, so 7.8. 7.8 centimetres equals little c. That's good. We can write that in now. 7.8. centimetres. Now to find A, that's a bit of a nuisance. I still don't know A divided by sine of A, but I could always use my 360 degrees in a triangle. I could say that angle A plus angle B plus angle C equals 180 degrees, the old 180 degrees in a triangle rule. So angle A would be 180 degrees. Take away B, which was 75 degrees. Take away C, which was 70 degrees. Now that means, what have we got there? That one and that one would be 145. So does that leave me 35 degrees? I hope that leaves me 35 degrees. So A is known now, which means my last step would be to go little a over the sine of angle A. Now in this one, I could either go B over sine B or C over sine C. Remember, I only need to work with 2 parts of the sine rule, not all 3. So I might go B over the sine of angle B. Little a is the unknown. We now have that angle A is 35 degrees. Little b was 8. And angle B, if I remember, was the one at the top, 75 degrees. So multiply by sine 35 degrees, and then I still would have 8 over sine 75 degrees. And definitely a job for my calculator to come back at. Here we go. Calculator back. Good. Now just make sure I can see that. So clear that last one. What do I want? Sine 35 multiplied by a fraction with 8 over the sine of 75. 4.75, round to 4.8 for 1 decimal point. 4.8 centimetres. So I'll go back and write that on my diagram. So A equaled 4.8 centimetres. And what did we say this one was? 35 degrees. We have solved the triangle because we now know all 3 angles and we know all 3 sides. Now, just as a quick check to make sure that I haven't done anything silly, it's always true with any triangle that the sum of 2 sides must be longer than the third one. Think about that for a minute, you'll realise why. So does 7.8 plus 4.8 exceed 8? Yes, it does. It works the other way too. I could say, what's the sum of 4.8 plus 8? 12.8. Does that exceed this one? Yes, it does. And finally, these two add to be more than this one. think about it for a minute. If you tried to form a triangle where two of the sides added to something less than the other side, it wouldn't be a very good triangle, would it? So that's just a very quick little idiot check to make sure that I haven't made a silly mistake. The numbers for those edges seem reasonable because they conform to that idea. That's enough for now, and this has been the sine rule. See you next time.